guys, welcome to the quartic formula. I busted out a new stick of high-grandma chalk for this one, so you know that it is very special. Actually, this is more so algebra and pre-calc based. No calculus or linear algebra or anything too crazy fun in this video. But I do want to cover this topic because it's quite interesting. So we're all familiar with, well, first let's let x be an element of the reals. We're all familiar with the natural logarithm function. So the natural logarithm function looks something like this. Let's draw a little Cartesian plane here. The natural logarithm function looks something like this. Okay. So it's essentially the inverse function. Well, it is the inverse function of the exponential function. So it's equal to 0 at 1, but it has asymptotes at x equals 0, and it doesn't have any other asymptotes. So essentially, it's defined for all x values greater than 0 on the real line. But today, we're going to consider the complex case. We're going to consider what happens when we have the natural logarithm of not a real number, but of a complex number, so natural log of z, where z is an element of the complex numbers, and z is equal to a plus bi, where a and b, that's a q, it's an a and b are elements of the reals. So, we're going to look at what happens in this case. So, the natural logarithm of a complex number. I'm actually going to go ahead and erase this and start on the top left, because I have a bad habit of starting in the middle of the board and then not having any room when I am halfway through the problem. So, I'll start here, and consider that we want to find the natural logarithm of a complex number. So, for lack of a better term, currently the natural logarithm of a complex number, natural logarithm of a plus bi, is not really in a form where we can do something with it. So, our goal at the moment is to ensure that we can, well, get it into a form that we can, again, for lack of a better term, do something with, to simplify it and maybe see if there's an easier way to calculate this. So, let's think about the complex plane. As we know, the complex plane has a real axis and an imaginary axis. So you have a complex component, real component. Imaginary component, real component. So, let's take the point a plus bi. So, this length is a, and this length is b. So if you're familiar with the idea of polar coordinates, polar coordinates essentially, so traditionally in math, you have it an x-axis to y-axis, okay? So you talk about coordinates in terms of x, y, right? Well, polar coordinates, just get rid of the x and the y and instead use some theta and an r to describe a point as an r theta pair. So we're going to use polar coordinates to sort of, well, to get this complex number in a polar form. So let's take this right triangle, and it has an angle theta and some distance with that hypotenuse r. So here's what we do. We take the sine of theta, which is equal to b over r. Okay, and we multiply both sides by r, yielding r sine theta equals b. We do the same thing with cosine. Cosine of theta is equal to a over r. R cosine theta is equal to a. Now that we know that a is equal to r cosine theta and b is equal to r sine theta, we can substitute it for a plus bi. So, a plus bi is nothing but r cosine theta plus r sine theta I. So this is where it gets really cool. We can factor out an I. Sorry, not factor out, factor out an r. So we pull r out. We get r times cosine theta plus I sine theta. This I is over here, I just move that to the front. It's the same thing, it's multiplication is commutative. Now, if you watch my last video, you'll remember that cosine of theta plus I sine theta is Euler's formula. And Euler's formula essentially states, well, it does state that cosine of theta plus I sine theta is equal to e to the I of theta. So we can take this and realize that it's the same thing and take our e to the I theta and plug it in for this. I have a video up with a proof of this formula, and it's a very useful one and one of my favorites in mathematics. So I'll plug that in, okay? So I'm going to go ahead and erase this part because we don't need it at this point, and I'll focus on this, and I'll start up here, okay? So this is nothing but r times e to the I theta. Equals r e I theta, right? So we get that a plus bi, this complex number, can be rewritten as r e to the I theta, right? So now we have it expressed in terms of r and theta, and you might be wondering to yourself, why are we doing this? Well, if this is true, then this must also be true. So the natural logarithm of a complex number in the form of a plus bi is the same as this, right? So we can just work with this. So you might notice that obviously there's an exponential function in there. Now the cool thing about the exponential function is that it's the inverse of the natural logarithm. So you may have a gut feeling that things are going to go well here, and the truth is that they will. So we can use our multiplication rule for natural logarithms that says that the natural log of a times b is equal to natural log of a, natural log of a plus natural log of b. So, using that here, we get that the natural logarithm of r e I theta is equal to natural logarithm of r plus natural logarithm of e to the I theta. Now, let's not do this obvious. Let's not look at this obvious expression right here. Let's instead focus on the natural logarithm of r. So we're looking for the natural logarithm of a complex number in the form of a plus bi, and while we could leave it as r, we prefer to have our formula for the natural logarithm of a complex number in, for lack of a better term, user-friendly form. Essentially, you have some complex number a plus bi, and you can just plug in the values that you have right there and get the output. So a way to rewrite r in terms of a and b is using the Pythagorean theorem. So a squared plus b squared is equal to c squared, or in this case r squared. And we square both sides, and we get that r is equal to the square root of a squared plus b squared. And then we can just put that in for r. So we get that the natural logarithm of r is equal to the natural logarithm of the square root of a squared plus b squared. Now, obviously, since natural logarithm and the exponential function are inverses, we end up getting I theta here. So, I theta. And now we have another evident problem, and that's the fact that we have theta. And this might seem like we've hit a dead end, but in all reality, all we need are the inverse trigonometric functions. So, let's take the fact that the tangent of theta is equal to b over a. And let's take the arctangent of both sides, or the inverse tangent. So let's take the inverse tangent of both sides. We take the arctangent of the tangent, we get theta. And that's equal to the arctangent of b over a. Right, so now what we have to do is plug it in for theta. So natural logarithm square root of a squared plus b squared plus I arctangent of b over a. So what we've just done here, it's very cool. We've just shown that the natural logarithm of some complex number in the form of a plus bi is equal to the natural logarithm of the square root of a squared plus b squared plus I times the arctangent of b over a. So let's do a little example using this formula. So let's say we want to find the natural logarithm of the complex number, let's say 2 plus 3i. Well, using this formula, we get that it's equal to the natural logarithm of the square root of 2 squared plus 3 squared plus I times the arctangent of 3 over 2. Okay, so we simplify this. That's the natural logarithm of 13, the square root of 13, because that's 4 plus 9 plus I times the arctangent of 3/2, and that is our answer. So the natural logarithm of 2 plus 3i is equal to the natural logarithm of 13 plus I times the arctangent of 3/2. So it's actually quite easy to calculate, assuming that you have access to a calculator, or you might just know the arctangent of 3/2 on the top of your head, off the top of your head. If you do, good for you, but I don't. So it's really interesting because start off with, we only use pre-calculus skills. We didn't use any skills that required even calculus, even calculus 1. We only use pre-calculus. And yet, these sorts of things, the extension of functions to the complex plane is not really taught in school, which is quite weird to me because, again, this doesn't require a lot of tools at all. So it just requires some basic properties of complex numbers, natural logarithm, and maybe, and knowledge of the exponential logarithm functions, which again, that's pre-calculus. So I find it very interesting how it's not really taught. It's also interesting because in school, it's sort of drilled into your head, the natural logarithm cannot have values less than or equal to 0 for the reals, and that is true. But it is always interesting to sort of extend these functions to complex numbers and see what comes out. So next time you think of a function and you only think of the real line, try thinking of the complex plane too. You might get something very interesting that comes out of it. As always, I appreciate you watching my videos, and if you enjoyed this one, please like, comment, and subscribe. And constructive criticism, as always, is welcome. Thank you, and have a good rest of your day.